Good morning and good afternoon. I'm Laurie Bagley from the Princeton Plasma Physics Lab, and I'd like to welcome you to the Federal Lab Consortium's Meet the Princeton Plasma Physics Laboratory, Powering Possibilities for a Clean Energy Future. I'd like to thank the FLC for hosting this lab showcase and our three presenters today, who will highlight the great work being done at our Department of Energy National Lab. Note that we will be answering questions today after each of the three presentations. Please put your question in the questions box. If we don't get to your question today, we will follow up with you via email. With that, I'd like to introduce to you our laboratory director, Professor Stephen Cowley, who will provide an overview of PPPL. Steve?
Hello, everybody. I'm going to speak for a very brief time here and just give you a brief introduction to the lab. The lab is one of the 17 national labs that DOE administers, and we're a relatively small lab with a focus on the physics and engineering and technology of plasmas. And that extends from our extensive research in fusion technology and working with some of the startup fusion labs, which you'll hear about later in this webinar, to the plasmas that help us make microchips and the plasmas that might make diamonds for the future and things like that. It's my great pleasure to introduce Emily Carter as our first speaker, who will tell you about some of the exciting new technologies that we're working on that exploit plasmas to help give us a clean future. So over to you, Emily.
Thank you, Steve. So hopefully everyone can see the screen, and I'm going to just jump right in and orient everyone first of all about plasmas themselves, and then move on to talk about new directions that the Princeton Plasma Physics Lab is taking just over the last few years under the leadership of Steve Cowley to expand the emphasis beyond fusion energy to other scientific discovery areas as well as applications in the areas of applied materials and sustainability sciences. So just to orient everybody, to remind people about what plasmas are, on the right you can see examples, the sun being the most obvious one. On the upper right, what you see is actual fusion plasma. Here is another example, the aurora borealis, as well as lightning, as well as compact fluorescence and neon signs. Basically, plasmas are ionized gases, a mixture of electrons and positively charged atoms and molecules. Our lab's focus, as you heard already from Steve, starts first of all with fusion energy. It's been working on fusion energy for more than 70 years with the goal to bring fusion power as a clean energy source, a clean, firm energy source for all. But in addition, what we'll talk about today are new avenues of research, and both basic and applied research related to building the technologies associated with information for the future, as well as sustainability for the future. Our lab's major strengths include obviously plasma science, computational science as well, how we understand and model these types of phenomena, engineering, and diagnostics and analysis. In terms of applied materials and sustainability sciences, which we're focusing on today because it's presumably less familiar, it's really a brand new direction the last few years. The question that you ask is, why are we reaching beyond fusion energy, and why now? Well, there's a national and, dare I say, global imperative to do so. In terms of material science frontiers beyond fusion, the lab is now working on next generation information technology that's critical to economic and national security, including working with companies, as you'll see in a moment, to see how we can help them understand the plasmas that they use to better make and manufacture next generation microelectronics chips that are generally based on silicon, but other materials as well as the new approach to information technology involving quantum quantum devices, so in particular quantum sensors and networks. So that's the applied material science side of this directorate. The second piece has to do with sustainability science frontiers beyond fusion. Obviously, fusion provides the future of firm, clean electricity that's fully decarbonized. But in addition, there are many other things that the lab's talent can, in fact, help with. It includes responding to the sins of the past, of the 20th century, namely the carbon dioxide and methane that is in the atmosphere that is causing the world to warm. And so we are thinking about and acting on the necessary need to remove carbon dioxide, to capture it, to convert it, and be able to, in the same way with methane, with natural gas, in order to essentially help move the planet onto a sustainable path with respect to reducing warming. That said, there is also the possibility that we may need to do even more than just remove carbon dioxide and methane. We may need to actually think about ways to reflect sunlight in terms of solar radiation management. In addition to worrying about the sins of the past, it's important to think about the 21st century and beyond, and how we live. What is our responsibility in terms of a civilization to become a sustainable civilization? And that really means getting to zero to negative carbon emissions in the future for all of our activities. So we started at PPPL 2 new initiatives. One that we refer to as electromanufacturing. The idea being that instead of the situation we find ourselves in today, which is that almost all manufacturing is powered by fossil fuels, instead removing fossil fuels from the equation and substituting clean electricity, either as electricity directly through electrolysis or through electricity creating plasmas that then can help with manufacturing. And then, as you can see on the right, also we have an initiative related to aerosol science for the climate, both for understanding the climate as it exists with natural aerosols, but also potentially understanding what would happen if the science behind aerosols associated that have been found to potentially reflect light. So what should PPPL's contribution be? Really, we're after leveraging our unique strengths in plasma and computational sciences, and we are absolutely working with and understand and value the importance of working with our local university, our M&O contractor, Princeton University, also with another national lab that sits in the Princeton ecosystem, the National Oceanographic and Atmospheric Agency's NOAA's Climate Modeling Lab, which is the Geophysical Fluid Dynamics Lab, GFDL, as well as industry and other national laboratories and universities. So we'll turn to each of these 4 areas briefly, and we start with microelectronics. Just to set the stage, industry invests billions in very large, complex machines that do manufacturing. About 50% of those involve plasmas for both etching materials and depositing materials. So insights that we can bring through our knowledge of plasma science into both the characteristics of the plasma, but also how plasma interacts with substrates, can potentially provide a competitive advantage to control and optimize processes for next generation microelectronics fabrication. Industry understands that basic research for them is too slow. It's not where they want to invest, but they understand the importance of it. And right now, those machines that exist in industry tend to have limited diagnostics. And so there is an opportunity that we have seized to have cooperative research and development agreements with the main tool manufacturers, including Applied Materials as well as Lam Research. And also we have a strategic partnership arrangement with Samsung. And this is to do the following. In the case of Applied Materials, for example, we are working with them, bringing to their deep ion etching processes of silicon wafers. We're bringing diagnostics that we have implemented on their state-of-the-art plasma etcher in California. And as a result, what we've been able to do is gather very important measurements and understand more deeply these etching processes that will help optimize the next generation chips. We developed a novel laser diagnostic for industrial reactors that we have patented, and we have these strong collaborative interactions, and both are, we have the ability to install diagnostics at the industrial location, but also industry is bringing their instruments to us. In future, we're going to apply novel laser diagnostics to monitor the control of the plasma in industrial reactors. Likewise, beyond experimental work, we have developed state-of-the-art modeling for plasma reactors that go all the way from atoms up to the reactor scale. And so this has allowed for a full kinetic treatment of plasma devices that are used by industry. And what we're doing now is moving from two-dimensional simulations that's a way to finesse the description to full 3D simulations and incorporating more realistic descriptions of electromagnetics and chemistry. We're looking for partners to maximize our efforts in these areas, and we have projects also that involve synthesis of nanostructured materials beyond silicon, and we're very interested in developing new partnerships in these areas. To show you a more general way in which one can partner with us, there is at PPPL a low temperature plasma research facility that has a whole set of different diagnostics that's shown here on the left, optical diagnostics that can characterize the plasma, as well as modeling, as well as a variety of plasma sources, innovative plasma sources. There's been so far more than 100 projects by users that cross academia, national labs, and industry, a variety of projects associated with material science, sustainability, plasma science, biomedicine, microelectronics, and quantum information science, with 50 peer-reviewed journal publications so far. We have a diverse set of users, and we're helping to develop a much-needed workforce for plasma science and industrial applications. In future, we're planning to extend this user program to R2 universities and to undergraduate colleges. Moving on to Quantum Diamond, that is our platform for quantum information science work. We're partnering with the company Element 6. It turns out that plasmas, again, through chemical vapor deposition, is the only way to grow this platform of ultra high purity and quality necessary for using quantum diamond for quantum sensors. And we have a group of people both at the lab and at Princeton University that are working at the cutting edge to understand both qubit performance all the way to plasma chemistry and how all of these things are coupled. Plasma chemistry itself, plasma surface interactions, materials properties, and the qubit performance. Turning to sustainability science, in particular to electromanufacturing, we have recently launched an Energy Earthshot Research Center through support from the Department of Energy that is on the sun, using plasmas to enhance hydrogen production by converting methane in the presence of catalysts to hydrogen and valuable forms of solid carbon, not nanostructured carbon, as well as taking methane plus CO2, the two greenhouse gases, and using plasmas to enhance the so-called dry reforming of methane that can lead to production of carbon monoxide and hydrogen, known as syngas. And from that, one can reproduce the entire chemical industry frankly. Syngas is usually derived from petroleum, from fossil fuels, and so this is a means of getting to feedstocks that industry needs without without coming from a petroleum source. This graphic shows that we are covering non-equilibrium energy transfer in kinetics and plasmas and using advanced diagnostics and in plasma chemistry, and looking at the interface between the plasma and the catalyst, as well as how the catalyst actually can affect the plasma. And so that is underway. We also have underway another Energy Earthshot Research Center that we're a partner with Oak Ridge National Lab that leads the effort. This one, the Hydrogen Shot Energy Earthshot Research Center, is led by PPPL. This one, led by Oak Ridge National Laboratory, we are studying how not using plasmas, but how we can use electricity, pulsed heating and quenching of samples in order to undergo chemical conversion. So this is using clean electricity to tailor both spatially and temporally how one can use electricity to heat samples in the most optimal way. This is just shows a little bit more detail about producing so-called turquoise hydrogen. It's not quite green hydrogen because it's coming from natural gas, but nevertheless, it's using up natural gas, which is a very potent greenhouse gas. So the idea, I've already told you, this is actually the beginning of what we hope to grow as a major initiative beyond just producing clean hydrogen, but also ways of using electricity to either through plasmas or electrolysis to produce the chemical feedstocks that are needed either from methane and CO2 or from waste plastics, for example, to not only produce hydrogen, but to produce other very important sources of chemical feedstocks, as well as solid carbon, as I mentioned before. And these are some of the kinds of techniques that are being used in our laboratories, as well as the kinds of collaborations that we have started just in this past year. With the Oak Ridge work, as I mentioned, we're using this so-called Joule heating, this non-equilibrium heating. And the idea here in this particular project is to focus on reducing the carbon intensity of a very important process that involves partial cracking of hydrocarbons to synthesize ethylene and propylene through electrification. Ethylene is an enormously important feedstock, especially for producing plastics. And the idea is that we're studying the science and engineering associated with these non-equilibrium processes. Our group is focused on the Joule heating. There are other parts of this Energy Earthshot Research Center that are focused on using mechanochemistry to access and control catalytic reactions that are much more rich and varied than those using standard thermal catalysis. Just to close, I want to point out that PPPL has partnerships involving technology transfer, and those partnerships go from industry to other fusion facilities for the fusion work that we do, other research institutions, government, and small businesses. And finally, in terms of partnership areas and agreements, we have, as I've mentioned already, CRADAs, these cooperative research and development agreements, strategic partnership projects, as well as technical services agreements. And I want to end by just pointing out again our core capabilities in plasma and fusion energy sciences, and I mentioned computational sciences, and all of these others in between are here as well. And if you're interested in working with us, please contact us at partnership@pppl.gov. So with that, I will stop sharing if I can, and get myself out of here. Am I still sharing? Is that a problem?
No, you're fine, Emily. So a couple of questions for you. Thank you very much, Emily. So with the cost of solar and wind energy getting down to lower than fossil fuel, what is the prospect for fusion energy to come in at comparable or lower costs? And is there a plausible timescale for getting to actual production of fusion energy?
It's a great question, and it is the 64, maybe I should say $64 million question. Solar and wind, the fact that they have reached parity and actually below is tremendously exciting. The problem is that solar and wind by themselves, because they're intermittent sources of electricity, are at this point still difficult to see how they can cover the entire landscape of electricity that is needed by our civilization. And as you saw in my discussion about electromanufacturing, the demands for electricity are going to grow tremendously as we transition off of fossil fuels. So there will be a need for highly energy dense ways of producing power. The real question is, as the questioner pointed out, is what's the time scale and the cost. And the exciting part of what's happening right now is that we are now at a stage where people are thinking about the work they do in terms of the scientific and engineering research, constrained by the cost, thinking about how we can reduce the cost of fusion power, which is not at parity. And we're not, first of all, we don't have fusion power yet. And the estimates at this point are that it is definitely too expensive. And so a huge part of the research that has to happen over the next couple of decades is to do both basic and applied research constrained by what we know the competition is. And I think the competition at this point is nuclear fission reactors that currently exist. And we have to be able to look at the cost of those and make sure we beat that cost. So the time scale is still, there are people that are saying it's less than a decade away. I think that is highly unlikely. I think it's much more likely that we will start to see electricity toward coming onto the grid from fusion more toward mid-century.
Okay, thank you. Another question for you. With fusion energy sources likely to be quite large generators of electricity, is PPPL doing anything on upgrading the transmission system for moving electricity around the country? For example, by a supplemental high voltage direct current national transmission network?
Great question again, and I think HVDC, high voltage direct current, is a terrific way to, as obviously the questioner knows, to make sure to have the lowest resistance possible. But that is not work that PPPL does. That lives in another part of DOE.
Okay, thank you. Another question, what other industries could benefit from the areas of research you've highlighted today? Specifically, are there AI applications to the areas you've talked about?
Great question again. Yes, in fact, we are using, and to great, I would say great advantage, we are using AI in our fusion research to help understand how to control the plasmas optimally, how to design the reactors optimally. I should mention in response to also to one of the previous questions that the main experiment at PPPL toward fusion is focused on what's called a spherical tokamak design. It's a smaller, compact design that should be cheaper than the other designs that that are being pursued more as science experiments right now. The large science experiment ITER that is in France, that is based on a normal tokamak design, which is more like a donut rather than a sphere. So we are paying attention to the cost, and we are using AI to look at designs for stellarators, for example. And I can't remember what else. Oh, actually, you wanted to know about other applications of some of the things I talked about today. So in the electromanufacturing area, we are also talking with BASF, for example, on a project that is related to using plasmas to make the cement manufacturing industry more sustainable as well. There are opportunities because cement, you may or may not know that cement, concrete releases in the process of making so-called ordinary Portland cement, releases CO2 to the atmosphere, and also has to be done under conditions which involve quite high temperatures, and those high temperatures have typically been provided through the burning of fossil fuels. But we're looking at whether or not plasmas, again, can essentially substitute for the fossil fuels in that case. There are other possible opportunities to use plasmas, I believe, to electrify parts of refining, ore refining, for example, and also for the creation of steel, for recycling. Of both, I mentioned plastics recycling, but I think but there's also, for example, a company that is using plasmas to recycle batteries, lithium-ion batteries. So there are a whole variety of different ways in which we can use low temperature plasmas to really green many industries.
Thank you.
I can't hear you.
Yes, okay, there we go. Great ideas on future applications of your technologies. And we, again, thank you for presenting today.
Thank you.
So with that, I'd like to introduce our next speaker, Dr. Ivan Ramadanov, Associate Research Physicist at PPPL. He will be speaking on confocal diagnostics applications in microelectronics. And with that, Ivan, please go ahead.
Yep. Thank you. Hello. Yeah, so my name is Ivan Ramadanov, and I'm working in UK Neuritis Group here at PPPL, and I'm going to expand on what Emily was talking about in applications for microelectronics and specifically for diagnostics. And this work is, like in our group, we're working on developing diagnostic tools in fields of ranging from microelectronics to space propulsion and so on. So today I will highlight the significance of plasma and diagnostics in industry, especially for microelectronics. And this work is a part of collaboration with an industry partner under PPPL Microelectronics Initiative. And I will focus on our work with low temperature plasma specifically, and using laser-induced fluorescence technique enhanced by structured light, and how we incorporated this structured light, making it possible to apply lab diagnostics for real industrial devices. Next slide, please. So why low temperature plasma? It is broadly used across many industries, as you can see here, and some key applications include etching and deposition or ion implantation, some electric propulsions, let's say similar to used in satellites like Starlink, and laboratory tools like panning discharge or magnetron, which helps us to better understand plasma physics of these devices. And the performance, lifetime, and efficiency of these industrial devices that I showed, it's closely linked to the properties of low temperature plasma, making its control and diagnostics extremely impossible for both industry and research. Next slide. So why is plasma control essential? And I will be giving two examples from microelectronics, which is a driving force of our computing power now. And recently it's moved towards atomic scale fabrication. And here on the left, you can see an example of high aspect ratio etching. It demands precise control over ion flow to make these deep, narrow trenches. This precision is critical, as it helps us to avoid defects in these things, and this kinetics is determined by plasma. And if you go next, then ion implantation system similarly relies on plasma to generate ions in ion plasma sources, and then these ions are directed towards the wafer surface with a magnetic system. And fluctuations in plasma can result in non-uniformities in material deposition. And this uniformity in general is paramount for both techniques. Say 1% of uniformity over 300 millimeter wafer is important for etching, and it's very challenging to achieve. And control of this minor fluctuations in plasma sources for ion implantation is yet to be achieved. It's all relies on plasma control, which can be performed through a real-time monitoring that will ensure that the processes are precise and uniform. Next slide. So what are our control parameters in plasma? What do we want to measure? So in microelectronics, here every process can be seen as a mixing of energy or electricity, plasma dynamics and chemistry, sometimes ion beams that are mixed in a precise ratios known as recipes. And this mix creates flows of ions and atoms that shape silicon wafer surface, and uniformity of this process is critical. For advanced control, the motion, flows, and speeds of these particles hitting the wafer surface are the key. And these factors connected with plasma parameters and the process outcome will inform better recipes. And we should measure them ideally without disturbing the plasma, and this is where laser methods are a perfect fit for such tasks. And if you go next, what is the issue with the existing lab diagnostics? We have a lot of them. And here you can see an example of a typical process equipment. And there are lots of challenges with implementing a diagnostic for this. It has limited optical access, reflective surfaces, emission, hazardous gases, and so on. It's not possible to directly implement such diagnostics. And our proposed solution is to use structured light beams to overcome these challenges. And next slide, please. So what do we measure? What is our diagnostic? Our main tool is the laser-induced fluorescence, which relies on two fundamental physics principles. First is the Doppler effect, and this is similar to how police siren speech changes when the car is passing you. But in case of light, it's not a sound, but a color or wavelengths of the color that's changing. And you can see here, if atom at the top is at rest, it will perceive wavelengths at one color, and once it starts to move, the color will change. And second important property is light absorption by atoms. Next, please. So when atoms have electrons at various energy levels, and these atoms can absorb incoming light, and this can excite electrons to higher energy levels. But this requires the light energy to match exactly the difference between these two energy levels. So if atom is moving, next, please. It will perceive the light with the Doppler effect, and it won't be able to have this transition, thus blocking the absorption. Next. Another important thing that after it's excited, there is an de-excitation process where atom release energy, and it's accompanied by emitting of the photon. Usually it's a different color, and this is what's called fluorescence. Next. So combining these two principles, we form a basic for us diagnostics. So by tuning the laser wavelengths, we can target species moving at certain speeds and excite them, and then measure this response fluorescence light. And notably, this fluorescence is uniform, meaning it emits in all directions. So we can put our sensor at any location, and you will see importance of this shortly. So what we do, we are mapping this response to a different velocities of atoms and ions. And next, please. So what we do, we reconstruct the velocity distribution function, which basically tells us how many particles move at which direction and at which speed. And this provides important, directly relevant to application information about atoms and ions. Next slide. So now let's discuss the specifics of the device that we are analyzing in our collaborative project. So this diagram highlights the device, which has every challenge that I've outlined before. It has a very limited optical access. It has reflective walls inside. It has a emitting surface inside. And with traditional LF diagnostic, we were able to measure only in the front part of this device, and back part is not reachable for us. And moreover, it's only 3 positions. This all motivated us to design a new LIF setup, and solution incorporates a confocal setup, which we enhanced with structured light, make it possible to measure velocity distribution function in these challenging settings. Next. So what is this structured light? So here you can see a diagram which shows all the possible degrees of freedom how we can control the light. And in a very simple analogy, you can make it to water. So water can stream in a very steady state flow, as shown at the top, or it can be in pulses like droplets, or it can even form spirals as this water sprinkles, and so on. With light, it's a similar idea. We can shape the light, we can form it, how it changes in time, and we can change its color, brightness, and so on. And by using such light in our diagnostics, we can extract more detailed information from an object that we are studying. Next. So in our research, we moved from a standard Gaussian beams that are usually used. We moved to a spatially shaping beams, generating these ring-shaped beams. And this enhanced our confocal approach, which I will discuss in more detail shortly. And such techniques in principle makes new ways for spectroscopy methods. Next. So now let me introduce our annular beam confocal LIF system, which allows us to overcome the problem with limited optical access. So confocal approach is frequently used in biological studies, but less so in plasma diagnostic. And it leverages this uniform nature of fluorescence emission I was talking about earlier, allowing for detection along the laser beam path. However, this leads to reduced spatial resolution and signal-to-noise ratio as laser beam interferes with detection. And by adopting an annular beam design, we separate the laser and fluorescence paths, as you can see here. So basically, a laser beam starts to form something similar to a waffle cone, and inside is our ice cream, our collected light. And this retains the advantage of confocal detection, but enhances both the signal-to-noise ratio and spatial resolution. And spatial resolution is now solely defined by the laser beam shape. And we tested this approach in our studied plasma source. We compared it to conventional LIF, showed a good comparison. And this will prove that it works in a real industry device. And next slide. So in conclusion, I want to show this image that is a test chunk reactors, which is used in laboratories. And even so it has a perfect optical axis, this performance is far from what's in industry. And by developing our diagnostics, we made it possible to do measurements in such devices through a minimal optical port, meaning that now laboratory studies can be brought closer to the industry, or we can even bring our diagnostics to the industry. And to recap that advanced diagnostics is critical for plasma control in industry and research, and that we developed annular beam confocal LIF for ion and atoms measurements, and we applied it to a real industrial plasma source, even so in laboratory settings. And we plan to expand structured light to other diagnostics relevant to plasma processes and beyond, such as laser Thomson scattering, two-photon LIF, and so on. And next. And this brings me to a vision of future directions of this research. So on the top left, you can see here our typical laboratory setup, which is bulky, complex, and not compatible with industrial applications. But if we mix it with a structured light, we plan to develop a compact, flexible, and industry-compatible sensor. And this sensor could be integrated into actual processing reactor, providing a real-time feedback system, which, if coupled with predictive modeling or machine learning, will result in more accurate plasma control. And in this work, we are open to any collaboration. Thank you. That's it.
Great, thank you so much, Ivan. At this point, we have no questions unless someone wants to, at the last minute, enter something. But no, Ivan, if something comes in after your talk, we will be sure to let you know, and we can follow up by email.
Yeah, sure. Thank you
so much. Our final speaker today is Dr. Michael Zarnstorff, who is the Chief Technology Officer of a company called Stellarex. Stellarex is one of PPPL's first spin-out companies, and Mike will discuss the company's efforts to advance fusion technology through a stellarator configuration paired with innovative developments in high temperature and high field superconductors. With that, Mike, please go ahead.
Thank you. I'm glad to talk today about the work that has brought Stellarex to where it is right now and our hopes for the future. Why don't we go to the next slide? We're just to say we're pursuing a path. We think will be the fastest path actually to come to a practical fusion pilot plant. Our goal is to develop fusion energy as a commercially clean energy source as fast as possible. And the importance of this is to mitigate worldwide climate change and also to provide a ubiquitous fuel that's available to everyone in the world without any significant siting restrictions, the typical siting restrictions we have right now. It requires that we come up with a process that's economically competitive, and we are targeting marginal production costs of less than $50 per megawatt hour and capital costs of less than $5 a watt. And again, we want a process that's globally accessible, because climate change has to be mitigated not just in the US, not just in the North, but actually worldwide. Another really important characteristic is it must be safe, and we want to minimize the activated wastes that are produced, because these are also key to being globally available and really useful in a broad way. This requires the integration and maturation of many new technologies, a large number of which have been pursued at PPL, but also at other DOE labs and at other institutions around the world. Why don't we go to the next slide? So we're focused on stellarators. It's a configuration that was actually the founding of PPL. PPL was the original director of PPL. Lyman Spitzer was the inventor of the stellarator configuration. It's a toroidal magnetic configuration. And that, in general, that has been the most successful approach to fusion so far. The point of it is that you confine the plasma. The plasma has to be about a temperature of about 150 million degrees in order to be actually fusing in the easiest fuel, which is deuterium and tritium. In a magnetic field, you get confinement in the direction perpendicular to the magnetic field, but you don't have confinement in the parallel direction. The plasma is free to move along the magnetic field. So you confine the plasma by confining the magnetic field into a torus. Stellarators are three-dimensional tori. They are not symmetric in the toroidal direction. That involves key insights. I'm not going to go into the details, but the big advantage that has is that you can make a magnetic torus with helical magnetic fields that does not require driving strong currents in the plasma. And that allows you to eliminate large instabilities, in particular the instabilities that cause the plasma to bash into the wall and leads to, in other configurations like tokamaks, leads to disruptions where the plasma terminates unexpectedly in a very quick time that causes large forces. But it also allows you to actually make configurations that have no external current drive. They don't require the input of power to maintain the magnetic configuration. That reduces the recirculating power and improves the efficiency of the overall system substantially, as well as reducing risks. This allows you to have smaller economical systems, which allows you to have smaller balance of plant. It also allows you to have steady state systems with essentially static magnetic fields, which makes it much easier to implement superconducting coils and much simpler to structure and design the coils. We've known this for a long time, and stellarators have had, because of the three-dimensional shape, they have a long history of concerns and of challenges about achieving adequate confinement, particularly of fast ions, because of the three-dimensional structure, the fact that there is no symmetry in a simple sense. They also require typically complex three-dimensional coils, which greatly complicates the engineering and the maintenance process and increases the cost of the base system. And so these have been issues of long research, of which PPL has been a leader. And this is part of why we are spinning out of PPL, is because of the experience that PPL brings. Next slide. So what is new? Why is now the time to pursue this? There's been a number of new results regarding stellarators that have come to fruition very recently. And amongst them is the Wendelstein 7X experiment in Germany, which started about 5 years ago. and has now systematically validated almost all of its design choices and design optimization activities that led to the specific design that they made. This includes orbit confinement optimization and neoclassical optimization that allows the neoclassical transport, the orbit transport, to be small and subdominant. It also results in turbulent transport that is well predicted by our present theoretical understanding. It's not the understanding that we had when they designed the machine roughly 20 years ago, but it actually is successfully modeled by the same theory and codes that have been used and developed in tokamaks and the rest of the field. And so it's actually in very good agreement with a theoretical understanding and modeling. The turbulence can be reduced by pellet fueling and by peaking of the density profiles as predicted by our understanding and by other machines. The energy confinement time that they have obtained is similar to tokamaks and other large devices of similar scale and characteristics. And the power and particle exhaust design has also been validated as being in correspondence with their calculations. So this is really a demonstration of predictability, of the ability to design devices and achieve the results that you designed for, which is actually a key for being able to go forward for a burning plasma system. Simultaneously, there's a device, actually W7X is a large superconducting coil system. There's another large superconducting stellarator in Japan called LHD, and they are nearing the end of their operation. They've been operating for 20 years, and they have achieved high plasma parameters in deuterium operation. So they've gotten peak ion temperatures and electron temperatures of about 10 keV, or about 110 million degrees. They've done it at low density, but nevertheless, they've demonstrated that stellarators can achieve those temperatures, which are necessary in order to achieve fusion energy. They've also been able to achieve high plasma pressure at high temperature, so the high normalized pressure relative to the field that they have. And so now in terms of dimensionless parameter performance, stellarators perform basically as well as tokamaks do, but they do so stably and without many of the complications that tokamaks have. And so we think they're ripe for pursuing in a predictable way to fusing plasmas. Go forward, next slide. What else is new? We now have improved theoretical techniques and theoretical understanding and optimization capabilities based on modern computers, including artificial intelligence. And these are being applied by the largest programs worldwide, specifically to stellarators and how to design stellarators to have even better configurations. Part of that is a project that's actually funded not by DOE or not by the governmental programs, but by the Simons Foundation in New York City and wider theoretical programs worldwide. These activities have produced new results and new computational tools for designing stellarator configurations. They've made new code systems, in particular codes called SimSopt and DESC, that can exploit the full power of parallel computing as we know it now, and new computational techniques. In part because this Simons Hidden Symmetries project is a synergy between physicists and mathematicians and applied mathematicians, computational mathematicians. So they brought modern mathematical activities and approaches basically to physical optimization. They've developed new methods to optimize and reduce plasma turbulence to improve plasma confinement. And they've developed reliable techniques for optimizing for fast ion confinement, in particular for confining the alpha particles that are produced by the fusion reaction and are used to sustain the heating of the fusing plasma in a sustained burn. So let's go to the next slide. This has resulted in remarkable theoretical progress in optimizing stellarators. And here you see the loss fraction for alpha particles in systems that are being calculated at roughly a reactor scale. And you're looking at them versus time vertically from devices like 7X that had rather serious fast ion loss, in the eventual understanding. And you look at the bottom, roughly half of the graph, where you see devices that were designed in the last 3 years by the Hidden Symmetries group and are basically down to negligible levels of fast ion loss, losses that can easily be handled at the wall. And so these have resulted in what are called, essentially perfect or ideal configurations that are actually essentially have no losses. And are these devices, or these studies have also resulted in coil designs that can actually produce these configurations that appear to be buildable and realistic. So this has been a quite enormous step forward, and very illuminating and also very hopeful. And you see there's many configurations now actually that we know have these systematically good properties. Let's go to the next slide. We've also had some developments that have resulted in new and simpler technological approaches. And in particular, there have been developments at PPL along these lines. PPL and actually also other DOE laboratories and other laboratories around the world. One part of it is the availability of high temperature superconductors, which are now available commercially and in substantial quantity. These allow higher magnetic fields, higher current densities, and operation at higher temperatures. All three of these are useful for actually making simpler and more compact systems. They allow the reduction in construction and operating costs, and opportunities to substantially reduce superconductor costs have been further from where we know now that we've identified ways to further reduce the costs. These HTS coils, or HTS conductors, and HTS techniques have allowed a general simplification of coil construction and of system maintenance. And in particular at PPL, we've identified, based on our experiences 20-ish years ago, and subsequently, we've identified a set of techniques that greatly allow the simplification of accelerator construction. And this is the use of magnetic dipoles in order to ease the construction and allow demountable maintenance. You can actually make the coils so they don't have to be three-dimensional. They need to be configured in a three-dimensional distribution. This can be done in 3 different ways, using permanent magnets, which is in many ways the simplest, but also using diamagnets based on bulk superconductors, and dipoles or saddle coils. And in all of these cases, these can be productively married to 3D printing and additive machining as a way to get highly accurate structures to mount the magnets. These techniques appear to be very favorable and have been now demonstrated in a prototype device constructed at PPL under LDRD funding, which is shown here in the bottom right. It's a small tabletop stellarator. It was rapidly constructed in approximately 1 year after the final design review, and is the world's first highly optimized quasi-axisymmetric stellarator and the world's first dipole stellarator. And we think that these techniques actually will allow us to actually have a much faster and simpler construction process. So our plan is to mature and integrate these technical developments and others that I haven't mentioned to develop a robust, safe, and low-cost fusion energy strategy and set of devices as fast as possible. We think that this will provide an attractive and timely method for the energy transition for society, eliminating greenhouse gas emissions for those who can implement it. In particular, we plan to use prototypes in an intermediate device called SX0 to, as quickly as possible, reduce the integration risks of these various technologies and advance the technical readiness levels in about 5 years. And after that, demonstrate an operational first-of-a-kind prototype commercial reactor we're calling SX1 that would produce hundreds of megawatts of net electricity, probably around 200, within approximately 15 years from now at an affordable cost. And we think this is actually foreseeable and doable. There's a number of choices to be made, but there are multiple choices in almost all items. So we think that a synergistic integration can be achieved.
While we're waiting, Mike, a couple of questions.
Sure.
I'm not sure exactly where to start. I won't have time for all of them, but if one does not want disruptions in fluctuations, does this mean one would need to run it continuously, independent of variations and shifts in demand, requiring some sort of moderation capacity, batteries, et cetera, to ensure optimal performance?
I mean, the details will matter, but stellarators basically can actually go up. No, go. This is an extra slide.
There was a conclusion slide.
There we go. Yep, this is it. So Stellarex is a spin-out of PPL and of Princeton University. We're licensing IP through Princeton University, but that was originated under PPL. And we're also building on the long history of fusion and stellarator research at PPL and Princeton. 2 of the founders are from PPL and 2 are not. Stellarex is built on partnerships. We're raising venture funds at this point to carry out the development, and we're not through with that for sure. And we anticipate continuing our partnership with PPL and Princeton. We also have a CRADA with Savannah River as part of an Infuse grant on tritium separation. We also are having some, and there's more coming, MOUs with other labs and potential vendors and also engineering firms. So there's there's a bunch of activities in terms of building a team and building a network actually to carry out the needed developments. So coming back, stellarators, because they don't require a large amount of recirculating power, they essentially have the lowest recirculating power for any of the fusion schemes of any type actually. We think that they will be more easily rampable and controllable actually to different power levels, because again, they don't require a large recirculating fraction. So it's not they basically don't have the large instabilities that cause in tokamak cases to cause you to have a relatively narrow operating regime basically, where you have fusion conditions, and in general are much more robust than tokamaks are in any case. And so we think that will make it much easier to be able to adapt the power level and control it.
Okay, great, thank you. Yvonne, are you still there? I have one question for you. Are you still on, Yvonne?
Yeah, yes.
So Yvonne, could you expand upon how your technology could improve manufacturing processes in the microelectronics industry?
Yeah, so as I said, our vision is to go and building sensors based on our device. So a sensor will be compact and it will be compatible with the real industrial devices. So it's potential to install it on a device and then feed the output of the sensor toward to the control software of these machines. And by measuring, let's say, flows of ions and neutrals, we can in real time see whether some plasma parameters needs to be adjusted or not, and how.
Great, thank you. Mike, note that I have 3 more questions for you, but in the interest of time, I'll send them to you via email and let you know who asked them.
I'm willing to stay on if people want to keep going.
Jamila, what do you think? Go ahead if anybody wants to hang on.
Yeah, we still have some people in the room if you'd like to answer the questions.
So Jamila, Mike, let me ask you a few more questions. What are the safety concerns when it comes to implementing fusion reactors into the real world power grid? And what kinds of technological advancements are needed to address them?
So the main safety concern is typically the tritium, keeping the tritium confined, keeping the tritium away from the public, and not having any substantial exposure to tritium. That's partly a matter of the forms that this tritium is maintained in, avoiding having it become oxidized and becoming tritiated water, where the biological activity is quite substantially larger, so roughly 10,000 times larger. And it's in part actually not making sure that the site is large enough to keep the public away from any accident that can be possible. That's a non-trivial safety concern, but it's actually something that there's a lot of experience with, in the sense that there's tritium used industrially in many, many places for lots of purposes. And there's lots of industry that has industrial handling equipment that has become available for managing tritium, and we plan to make use of it. There are some parts that need to be closely integrated with the fusion system that will need development, and there are parts that I would say the integration is still the best way of integrating is still to be worked through. So there's multiple choices, and we need to figure out which one's going to be most attractive. And that's in part, that's the Savannah River Infuse project that we're doing right now is related to that. But there will be additional development work on that regard. So the tritium, just like hydrogen, has a tendency to diffuse through metals, depending on the choice of your metal. And you have to have active ways of containing it, which is not that unusual. Again, there are standard ways of doing it. It's a matter of integrating it together. And it's not the same as running a plasma physics experiment. And so that's a specific thing. I should note that one of the things that I think is important is that the fusion community as a whole, including PPL, has now had some experiences with tritium. So TFDR, when it was at PPL, ran in tritium for over 4 years and ran closed loop, recirculating the tritium. And I was part of the physics side of those experiments, but I have friends that were part of the tritium control side and had some of those experiences.
Great, thank you. One final question, Mike, and then I think we can wrap up for the day. What happens if there is a sudden interruption on the supply of electricity to the system or in the external grid connect such systems to the locations needing energy? Basically, does a fusion reactor have a safer sudden shutdown path than nuclear reactors?
Yeah, I would say yes. So the confinement, so there's two parts of that, I would say. The one is that the plasma itself, has a confinement time that's on the order of seconds, 1 to 2-ish seconds. And so you can put the plasma out in a controlled and safe way, or it can go out on its own, especially in a stellarator in a controlled way in the time frame of a couple of seconds. And so the amount of energy and the amount of energy that's in the plasma is just not that large. And so that's a big difference between fission and fusion. Fusion has a year, roughly a year's worth of fuel in hand. Fusion has a couple of seconds of fuel in hand at any time. The superconducting coils have also a substantial amount of stored energy, but you end up wanting to design the coils, and you can design the coils such that that energy can be completely contained and thermalized within the coils themselves without damage. And you want to do that. You want to make, it's called making them quench safe. And it's important to do that, but that is actually done very commonly in superconducting coils, and there are methods for designing for that.
Great, thank you. Thank you everyone for your time today. Thank you to our 3 speakers, as well as Steve Calley, our lab director. Going forward, if you would like to reach out concerning any of the topics, please email us at partnerships@pppl.gov. I'm sure FLC is also a conduit for contacting us as well. So thank you very much.